Okay, hi, this is Mr. Cook. Let's talk about average rate of change, specifically just what is the average rate of change. Okay, so you think of the average rate of change as essentially being like a slope. Slopes work really, really well when you have just a line that you're graphing. It tells you how much something changes from one coordinate to the next. In the case of a slope in a 2D system, then it's just the change in y, delta y, over the change in x, so delta x. All right, and we just made a little ratio of it, delta y over delta x. It was really nice for linear lines because then we could predict where another point would be on the line. Okay, so that was really helpful for linear equations or slope. Okay, but what if we want to predict the outcome of something, or the position of something for a line that's nonlinear? Okay, so let's say that we don't have an equation for this. We just have some weird little like curved line. Okay, up to this point, what we have been using is kind of forcing or spamming the slope formula on this curved line. That's what average rate of change is. And I'm not a huge fan of average rate of change, to be perfectly honest with you, but this is a really basic tool that we use to predict some sort of rate at a given point. Okay, we just find its average. You guys will learn in calculus how to find an instantaneous rate of change really easily by finding a derivative, and that's foundation. That's based off of the difference quotient, but you won't have to worry about that for another basically year and a half. Anyways, so we spam the slope formula onto some curved graph, and basically we do the same thing that we did with slope. You have one coordinate here, one coordinate over here, and then you find the change in the y value over the change in the x value. It's not great for predicting where another coordinate might be. Like, if I go along the x-axis over here, if I used this as a predictive line, it put me over here, when in actuality along the curve I'm over here. So if the curve was reality and the line was like some sort of prediction, it would give me like a little bit of error in between those 2 points. That's why average rate of change isn't great. That's why we prefer calculus to that and finding instantaneous values. Okay, so the formula for average rate of change looks way more challenging than it actually is. It looks something like this: f of b minus f of a over b minus a. Okay, so what does all this stuff mean? This basically means that we are finding the average rate of change, or the slope of some curve, the average rate of change of that curve from one x value to another. In other words, spanning some interval of x values. So you will be given the following things when you're asked to find the average rate of change. Here's what you will be given. You will be given specific x values that you're supposed to find the average rate of change for. Okay, so you'll be given an interval, and it'll be a closed interval, and it'll have 2 values that are its extremes. So these are just x values that you're looking at, okay, when you're given some sort of example. So here's an example of something you might be given. Maybe you're going to find the average rate of change between -3 and 7 of some function. So that leads us to the other thing that you're going to be given, a function. So you'll be given just some function that represents the idea of this curve or the graph, whatever you're trying to graph out. And you're supposed to find the average rate of change, that slope between the 2 points. So again, we're given the x values here, and we'll be given a function. I'm just going to make up a function right now. F of x is equal to, and let's say it's, x to the third plus 2x squared minus 5, or whatever. Okay, so I just made up some equation over here. We still do the average rate of change the same exact way no matter what, okay? And remember, it's just the slope, okay? So the way that we wrote out the slope formula was y2 minus y1 over x2 minus x1. And we wrote this out because we had, when we learned this formula, we were just in, pre-algebra class or maybe an algebra class, and we were just learning about mathematical notation. We didn't even know what a function was when we learned that slope formula. So this is just sort of like an upgraded version of the slope formula, okay, using function notation. And remember, this function notation is something that we've become a little bit more familiar with, having done difference quotient problems in the past. The b value is just something that you plug into the function. The a value is just something you plug into the function. Either way, you just end up with numbers all the way around, just some number that we're plugging into all this stuff, okay? All right, so let's use the formula over here on our example and find the average rate of change for this scenario. So here's how easy it is. Remember that these are the x values of some interval, okay? It gives us the starting point and the ending point that we're trying to find the slope between, okay? So these are the x values. So if I'm given two x values, I need to find the corresponding y values before I can do the slope. So here's what I do. I take -3, which is the starting point over here, and I plug it into this function, okay? So I need to find f of -3. In other words, I plug in -3 for the x value. So -3 to the third power plus 2 times -3 to the second power minus 5, and then I evaluate it. -3 to the third power is -27. -3 squared is 9, so that's plus 2 times 9, and then minus 5. Okay, so -27 plus 18 minus 5. -27 plus 18 is going to be a -9, and -9 minus 5 gives me -14. So -14 goes right over here. Now I got to do the same thing with 7 plugged in there. Okay, so we've got f of 7 is equal to 7 to the third power plus 2 times 7 to the second power minus 5. So 7 to the third power, that's, let's see here, 7 times 49, that'd be, let's see, I'll just use my calculator, what the heck, I'm trying to do too much in my head. All right, so 7 to the third power, I should have this memorized, so shame on you, Mr. Cook. 343, okay. So 343, and then 7 squared is 49, 49 times 2 is 98, and then minus 5. All right, so if we add these two numbers together, we get 441 minus 5, so that'd be 300, oops, sorry, subtracting 5, come on. 4, geez. And then 41 minus 5 is 36, so 436. So 436 is going to be our y value for that x value of 7. And then, like I said before, this is just the slope formula. So we found, we know what our a value is. We know what f of a is equal to. This is our b value, right? And then this is our f of b value. So we plug it into the formula and we get the following. The average rate of change is equal to, and then it's going to be f of b minus f of a, so 436 minus f of a, which is -14, all over b minus a. So the b value is 7, the a value is -3, so minus -3. And then we just keep evaluating this ratio. So 436 plus 14 gives me 450. And then 7 plus 3 gives me 10. And then if I divide out these two numbers here, I get 45. So my average rate of change is going to be 45. And that is, this kind of, not super challenging, but it's a cubic expression. This is the example using a cubic expression. I think the ones in the book aren't terribly bad. It's still just the same thing. You just take the a value and the b value, plug them into the function, whatever it is, and then just do the slope of the x values and corresponding y values. And you just get some numerical value, and that's it.